Okay, good evening, everyone. I hope you can hear me. Please give a reaction if you can hear my voice. Looks like our number is quite few today, so all right. We are going to start anyway. So the plan for today was UGRC 110. However, the one supposed to handle it is caught up in a little something, so he will start at 8. So we would like to occupy you till 8 by doing a little statistics. Since we know statistics is one of the courses that can far, like what do we say? It comes later in the exam. So yes, we've been holding it off, but can still tackle it a little just for time's sake. And then when it's 8 o'clock, we continue with UGRC 110. So they will be solving some questions, past questions in UGRC 110. But before then, as I mentioned earlier, statistics. The last time we met in statistics, we were almost done with the lesson 1A. Let's see. Right. Okay, so then we were somewhere around here. Yes, we were actually tackling this very question over here. We were supposed to work out some values. We were supposed to solve for a few things. I believe we did all these questions actually. Yeah, we did all these questions and we came by the answers too. So today we are going to proceed from where we left off. We have discussed a lot of concepts in section 1A. Hopefully today we can end it and move on to section 1B. So let's redo this example so that we can recall what it was we learned the last time. All right. So then the example says that suppose that events A, B, and C have properties. P of A, probability of A is equal to, 1/2. That of B is 1/3, and that of C is 1/4. Furthermore, we assume that the intersection of A and C is 0. So there is no intersection for A and C. There is no intersection for B and C. And the probability of having an intersection of A and B is 1/6. So it means there's an intersection for A and B. Using the agents of probabilities and then the properties that we learned about, we have to find out the probability of getting the complement of A intersection B. So what this means is we just calculate A intersection B and then we subtract it from 1. Yeah, I believe you remember the properties we discussed the last time. And I mentioned earlier that when you see the N like this, the OR operator is used to say that we do additions. But whenever you see AND, for probability AND, we do multiplications every time. So this question says that we have to find the complement of the probability of A intersection B. In other words, we are finding A and B, and then we take that out of 1. So a quick recap for our previous lesson, we are going to use this example to do that. So let's see how that's supposed to be. All right, so let me share my board quickly and then let's dive right into it. We have so little time, so I don't want to. All right, so then question 1 was we have to find the probability of A intersection B or complements like this. So we are supposed to find the probability of intersection B first, and when we are done, we subtract that from 1 to get a complement. So I believe you remember this from when we were discussing the axioms last week. So let's see how that works. So in order to find the probability of A intersection B, we need to know probability of A, and according to the question that was given to be, so it says that the probability of A occurring, well, where is it? Furthermore, assume that the probability of A is equal to 1/2. And then it's also mentioned that the probability of B is giving us 1/3. Therefore, the probability of A intersection B, which is probability n, remember that. So that's what you go by whenever you see an intersection or finding A and B. You just multiply both probabilities. So the probability of A intersection B is going to be the probability of A, which is 1/2, multiplied by the probability of B, which is 1/3. So multiplying these two values gives you exactly 1/6. So this is the probability of A intersection B. But remember, the question wants us to find A intersection B complements. So we have to find the probability of A intersection B not happening. Remember, the total probability is always 1. So if the probability of A intersection B happening is 1/6, the probability of it not happening is going to be the total probability minus 1/6, which is just going to be 1 minus 1/6. So the probability of getting A intersection B or complements is going to be total probability, which is 1, or the chance. So total chances, that's 1, the certainty of minus 1/6, like this. Subtracting that gives us the value 5/6. So that is our answer. I believe you can still see my screen. Yes, I believe you can see my screen still. All right, good. So I hope that was clear. Let me allow all your mics so that you can mute when necessary, and then and it will take it will reduce how much time we are spending on all these things. Please, now that our mics are allowed, let's be mindful of the muting and unmuting, so that we try to not cause distractions in the class. Thank you. Okay. Let's proceed. So now the second question asks that we check the probability of, this is what it looks like. So it says probability of A intersection B complements. Now you see the difference between this one you see here and then what you saw the first time, which was probability of A intersection B or complements, is for this one, the first one right here, we are supposed to find the probability of the intersection of A and B not happening. But over here, you're supposed to find the probability of A as well as the probability of B complements, both happening at the same time. These are two very different events, so then you should take good notes of how they look, so that when the question comes, you will not solve it wrongly, not due to the fact that you didn't know, but then due to the fact that you overlooked details. All right. So now, in order to find the probability of A intersection B complements, we do the same thing we just did. We first have to know the probability of A, and then we have to know the probability of B complements. So now let's see if the probability of A was stated in the question. The question stated the probability of A to be 1/2, so that is a given. But it didn't state the probability of B complement, so we have to find B complements. And according to the properties of probability we learned one of the properties that's the probability of an event A occurring is given as probability of A. The probability of A not occurring, in other words, A complement, is going to be total probability, which is 1, minus probability of A occurring. So the same applies to B. We know that the actual probability of B is given as 1/3, according to the question. But then the probability of B not occurring, or in other words, B complement, is going to be 1 minus 1/3. And that gives us 2/3. So now that we know the probability of A is 1/2, and then the probability of B is 2/3, we can now calculate the probability of A intersection B. So remember, intersections are probability n. Therefore, we are going to take 1/2, that's probability of A, times probability of B complement, which is 2 out of 3. 1 multiplies 2 and gives us 2. And then 2 multiplies 3 and gives us 6. So simplify that and you have 1 out of 3. So that is probability n for these two values. And then let's see the third question. Third question says that we are to find the probability of A union B or complement. So then it means you are finding the probability of A union B not happening. So just like the other ones, we first find the probability of A union B, and then we subtract it from 1 to get the complements of probability of A union B. Probability of A union B is probability n. And we know that in probability, it's probability or, and we know that in probability or, we do additions instead of multiplication. So we just take the probability of A occurring, which is in the question giving us 1 out of 2, and the probability of B occurring, which was given in the question as 1 out of 3. So then the probability of A union B is going to be probability of A, which is 1 over 2, plus probability of B, which is 1 out of 3. Let's work this. We need an LCM since we are working on fractions, so 6. And then 2 goes here, 3. 3 times 1 is 3. 3 goes here, 2. 2, 1 is 2. I believe these are basic facts, so we know them. And our answer is 5 over 6. So this is the probability of A union B, like this. But the question didn't ask for this. It asked for the complement. So now we know the probability of this occurring. So what's the probability of this not occurring? That's going to be the total probability minus this value. So then the actual probability of A union B, all complements, is going to be 1 minus 5, 6. Yeah. Okay, 1 minus 5, 6, like this. And then that will give us, so let me create room for this. 1 minus 5 out of 6. Like this, okay. So then LCMs. 1 goes here, 6, 6, 1, 6 minus 6 goes here, 1. And then that's a 5. So 6 minus 5 is 1, and then you're left with 1 out of 6. So these are just basic facts, just like what we learned the last time. In as much as these are basic facts, if you have any questions, please be sure to ask, okay? We tackled these things last week, but it doesn't mean we tackled this in our last meeting, but that was a long time ago, so it's understandable that you ask questions. However, for the sake of time, I'll plead that you desist from that. Okay, we proceed. The fourth question says we should find the probability of A complements and B complements all occurring. So then let's do that. This means that we need to find probability of A complements, multiply that by probability of B, since this is an AND probability. So probability of A is 1 over 2. Therefore, the probability of A complements is going to be 1 minus 1 over 2, and that will give us 1 over 2 if we do the subtraction right. Now, the probability of B, so we know probability of A complement is 1 over 2. Let's keep that in mind. Now, the probability of B is 1 over 3. So the probability of B complements is going to be 1 minus 1 over 3, which is equal to 2 out of 3. So it's equal to 2 over 3. Okay, I have little space here, so I'm barely managing. Good. So since we know that the probability of A complement is 1 over 2 and that of B complement is 2 over 3, then the probability of A complement intersection B complement is just going to be the product of A complement, which is 1 over 2, and B complement, which is 2 over 3. And what that gives us is 1 times 2 is 2, and then 2 times 3 is 6. Simplify that and you're left with 1 over 3. Now, it's important that you note that, you see, last week we mentioned that there's a property that says sometimes some events may have intersections. For events that actually have intersections, that we call dependent probabilities. So for events that are dependent probabilities, whenever you work them, you are going to have to subtract a number that acts as a middle number. Like in the case of tossing, a multiple of 3 and then tossing an even number on a Ludo die. You see the multiples of 3 are 3 and 6 on the face of a Ludo die. And then the what do we call it? Even numbers are 2, 4, and then 6. What this means is that 6 becomes a number that occurs in both sets. Therefore, if you are to calculate the events of both, if you are to calculate the events of multiples of 3 happening and multiples of, and then even numbers happening, sorry, you are going to have to make sure that 6 only appears once in your combined sets. And in order to do this, you are going to have to eliminate one of the 6s from the sets. So what this means is that you're going to subtract the intersection. So if you remember the last lesson we had, we mentioned something like this, that given that the probability of A intersection B is not a null set, then if we have A intersection B is possible, then it means that to calculate the intersection, so let's list the elements of the sets that we are using so that we can see this more clearly. On the face of a Ludo die, we have all the values 1, 2, 3, 4, 5, and 6. Now let's say A is a set of even numbers. From the face of the Ludo die, we are going to have 2, 4, 6. And B is a set of multiples of 3. So then we are going to have 3 and 6 on the face of a Ludo die. If we are supposed to calculate the probability of event A as well as B occurring at the same time when we do a picking, the sample space we are going to have is going to look something like this. So then we are going to see the possible values we can get when we pick A and B at once, or when we pick something from A and B. The sample space is going to look, or all the possible outcomes are going to look something like this: 2, 3, 4, and then you see there is a 6 here and then a 6 here. Now, in order to avoid the 6 occurring 2 times, then we are going to have to remove 1 6 from this, right? So that we are left with 6. This explains the property that we looked at the last time. The property that said that whenever there is an intersection, you subtract the number of times the intersections occur. And that's what we just did here. So then if I want to calculate the probability of even and odd numbers occurring, this is what the working will look like. So now I have shown you what the sets notations are like this. Now let's see what the actual working would look like. So then the probability of A occurring, remember that the probability of A occurring will mean number of A present over the total number of elements in the sample space. So then let's see, A is a set of even numbers, that's 2, 4, 6. So then that makes it 3 out of 6 elements. In other words, 1 over 2. The probability of B occurring, so this is A. The probability of B occurring is going to be, how many elements are in B? 2 out of the total number of elements, 6. And that gives us exactly 1 over 3. So then if we want to find the probability of A intersection B, then we are going to have to take the probability of A, which is 1 over 2, and multiply that by the probability of B, which is 1 over 3. However, due to the fact that we can see an intersection, which is 6, occurring at both sides, we have to make sure that 6 only occurs once since it's the same value. Therefore, we are going to subtract the number of intersections that are present. And in this case, there is just one intersection, that's 6. So then 6 is 1 out of 6 chances. So it will look something like this. So our probabilities value, this is what it's going to look like. Okay, so then this one will yield a result of 0. So it's going to be 1 over 2 times 1 over 3. That gives you 1 over 6. And 1 over 6 minus 1 over 6 gives you a 0. So for events that are not independent, the events that have an intersection, a true intersection, in order to calculate the probability of them occurring, you have to subtract the number of intersections that are present. All right, so keep that in mind. Final question says that we are to find the probability of A union B union C. So then the probability of A union B union C is the probability of A, B, C. like this. So since the probability of A or B or C happening is just the combined probability of A plus probability of B plus probability of C minus a possible intersection if there is any. So the probability of A was given to be 1/2. That of B and then that of C is 1/4. So now we have to calculate the probability of all these three events occurring. That means you have to calculate the sum. That's basically, since it's A union B union C, so A or B or C. So 1/2 plus 1/3 plus 1/4. Now, in order to do this one, we have to check to see if there were any given intersections at any point or at any point in time. So go back to the question. It's mentioned that probability of A intersection B, A intersection C, was 0. So it means there is no probability of A intersection C. There was no intersection of B intersection C. And there was also no intersection for all three. But we know that there was an intersection for A and B. So then there was one intersection. So the probability of A intersection B was given as 1/6. So then the probability of A intersection B, let's write that here, 1/6. So that's A intersection B. Keep that in mind. It's 1/6. So then knowing this, it means if we want to find our probability, we are going to have a particular value occurring 2 times. We're trying to find the number of times the thing can occur, and then there's an event that is occurring 2 times. The same event occurring 2 times. So since it's the same event, then the best you are supposed to do is take one of it out so that it's just left with the single one. Okay, so according to the question, that event in this case is B equals 1/6. So then the probability of that intersection is 1/6. We subtract the intersection from it, minus 1/6 like this. So then let's find the sum of these values. You know how to do addition of fractions. So you take your LCM, in this case it's 12. 2 goes into 12 6 times, and 6 times 1 is 6. 3 goes here 4 times, and 4 1 is 4. And then 4 goes here 3 times, and 3 1 is 3. So like so. So then your answer is going to be 6 plus 4, that's 10, and 10 plus 3, that's 13, all over 12, and minus the 1/6. So then let's create space for this. 13 over 12 minus 1/6, 13 out of 12 minus 1/6. So then we work this further. Remember that 1/6 is the intersection for A and B, so it has to be subtracted to avoid recording double values. So then our LCM is 12, and then 12 goes here 1 and goes into and multiplies 13 to give 13. 6 goes here 2 times and multiplies 1 and gives you 2. So 13 minus 12 minus 2 gives you 11, and then you're left with 12 right there. So then the probability of A union B union C, when you are working that, you have to consider if there are possible intersections and subtract the number of intersections present, or subtract the probability of the intersections occurring from the sums that you will generate. And this will lead you to the final answer you are looking for. So these were the questions from last week's session, right? So we are going to proceed, and then we have about 26 minutes, and I believe we can do the next lesson as well, 1B. All right. Okay, so we proceed now. Okay, so then you can see the answers are there, intersection B. Now they followed various approaches. For example, when solving for the other questions that required intersections, they were applying laws like De Morgan's law, and then they still arrived at the same answer, 1/3. So this is why the laws also help you. However, if you go with the word probability or and probability and you know that for ors, you're always doing additions, and for ends, you're doing multiplications. And also consider if there are intersections and subtract them, you always arrive at the correct answer. All right, so we proceed. This example says in the source of a fair die, we have to find the probability that the result is even or
A lot.
divisible by. So that's what we just
A
did.
lot.
It's either even
A
or a
lot.
multiple of 3. And we just figured that
A lot.
out and subtracted the intersection. The intersection was going to be the number 6 because
Hello, sir, Mr.
for
Please.
events that are even, so look here closely. The even numbers are 2, 4, and 6. And then the multiples of 3, or numbers that can be divided by 3, are 3 and 6. All right, Mr. Interiba.
Hello, sir.
And our intersection is 6. Therefore, we add the two values, that's the probability of A and B, then we subtract the probability of the intersection occurring, that's 2 over 3. Okay, so Mr. Interiba, please, you may unmute and then ask your question.
Hello, sir.
Yeah.
Hello. Please, can you go back?
Sorry, please come again.
Can you go back to the first example 1? It's like the answer the answer they had here was 11 over 12, and we had 13 over 12. Yeah, you passed by the place.
Oh, no, we didn't have 13 over 12. It was 13 over 12 minus 1 over 6, and that's 11 over 12.
Oh, okay. Okay.
Okay, so then you might have missed that. Okay, so what happened is this: there is an intersection. Okay, the intersection was mentioned to be the value 1 over 6. So then if you find the sum, you are going to get 13 over 12, but you have to subtract the intersection. If in mind, you know that 13 over 12 is not impossible. It's not a possible probability because that's a value greater than 1. It's supposed to be between 0 and 1, so that's wrong. So you have to subtract the intersection, and the intersection happens to be 1 over 6. So after we got 13 over 12, we subtracted the 1 over 6, and that gives you 11 over 12. So please, does that answer your question?
Okay, well monetization.
Oh, okay, I'm sorry. And then it's here. Look at it. This is the screen. Let me share that so that you can see it. I mentioned that before that I am using 2 devices. Going back and forth to the board is a little of a struggle, but let me just share my screen and then get back to it. I believe you can see the screen I'm sharing now. Let me see. All right. So I believe you can see my screen now. So let's look at the board here. So this was the last part of our calculation. So we initially solved and then we got 13 over 12 minus 1 over 6. And I said, let's use more space. Remember, 1 over 6 was the intersection. So subtracting the intersection is what gives you the value 11 over 12. So Mr. Interova, please, are we good now?
Yes, sir, we are good to go.
Thank you, boss. Thank you for pointing that out. Okay. Now, right back on topic, we continue. All right. So now here's another that says 2 events are said to be equally likely if the probability of A occurring is the same as the probability of B occurring. So event A is said to be more likely than B if the probability of A is greater than that of B. So what this means is if I take a pair die and I decide to toss it, the probability of me obtaining an even number is 1 over 2. That's 3 out of 6 faces. And the probability of me obtaining an odd number is still 3 out of 6. That is 1 over 2. However, so what this means is that the probability of an even number occurring or an odd number occurring are equally likely. So the probability of an odd number occurring is the same as that of an even number occurring since they both yield the results of 1 over 2, 1 over 2. However, if it happens that I want the probability of even numbers occurring, and I want to compare that to the probability of multiples of 3 occurring on the face of the die, the probability of even numbers occurring is going to be 1 over 2. But we know that the multiples of 3 on the face of a die are exactly 2 out of 6. That gives us the chance 1 over 3. Therefore, the probability of the first one occurring, 1 over 2 is equivalent to the decimal 0.5, whereas 1 over 3 is equivalent to the decimal 0.333. So you can compare them to see that the probability of an even number occurring is far greater than the probability of a multiple of 3 occurring when a fair die is tossed. So that's what it says. So if you say they are equally likely, then it means they have an equivalent probability. However, if one's probability is greater than the other, then it goes to say that that probability, the chance of that event occurring is more likely than the chance of the other occurring. So now it says if all the outcomes of a random experiment consist of n equally likely simple events, then the probability of an event E made up of k simple events is probability of E is given as k over n. What this means is just like the face of a die issue. We know that the probability of a 1 occurring is the same as that of a 2 occurring, is the same as that of a 3 occurring, all the way to the end. Therefore, for every event on the face of the die, the probability of it occurring is going to be that event A over the sample space or over the total number of possible outcomes. Okay, so then this is no new thing. So it says the proof is left as exercise. So you can check that with the face of a die issue. You can check probability of 3 occurring and check the probability of a 4 occurring, and you realize that they are all the same value. All right. So now this particular question is a question that requires you to take into account conditional probabilities and all. Now it's a fairly simple question to work because most of the job will be done by a calculator. Yes, most of the job will be done by a calculator. However, before we tackle it, I'd like us to go and then tackle conditional probabilities and get to understand the whole image before we come back to this. So I hope that our lesson permits us, or the time permits us, to go and then do all that before we come tackle this question. Expectation of random variables. Sorry. So expectation is a fairly simple concept. And then it says an important notion in statistics, the expected value or expectation of a random variable. Expectation of a random variable is the long-term average of the random variable. So for instance, imagine observing many thousands of independent random values from the random variable of sets of interest. You take the average of these random values. The expectation is the value of this average as the sample size tends to infinity. What this means is, say you are given a set of values. The probability of each single value occurring differs. The longer the probabilities keep happening, the closer we approach the certainty of certain events. The expectancy or the expectation tells you how likely it is for a particular event to happen as compared to the others. It can be taken as the sum of all the events over the total number of events there, or sometimes it can be the expectation for a particular value. So now this one says if x is a random variable distributed as probability of x of a particular value or the function of x, then the expected value of x, which we will denote as the expected value of x into bracket, that's E of x, will be defined as the sum of all the values of x. Now this one, I want you to look at the formula, and then when I'm done, I'm going to rephrase it in words so that there will be an easier way for you to view it. Okay, so there's the sum of all the values of x over the sum of x times the frequency. That's all there is to it. I told you that sometimes the formulas are hard to interpret, but then in the example to come, you will come to understand what this just means. So now this one says, consider a class of 24 students. Suppose that 5 of them are 19 years old, 7 are 20 years old, 10 are 23 years old, and 2 are 17 years old. Let us denote U, which is the mean age of the class. That is, remember to calculate the mean, it is just every single individual value put together over the total frequency. So then we have 5 over times 19 plus all that, and it gives us 20.79. So now it says that let x be the random variable taking the distinct ages as values. That is, x is equal to x1, x is equal to x2, x is equal to x3, x4, where x1 is the first age, x2 is the second age, 20, x3 is the second age, 23, and x4 is the fourth age, 17. What Hello, I'm sorry for that. Please, can you hear me? Give a reaction if you can hear me. All right, sorry for that. Please, can you hear me? A call came in, so I had to attend to it. But please, if you can hear me, can you give a reaction so that I know we can proceed? Wow. I can't tell if you cannot hear me or I'm the one who is not speaking into my mic. It's a network. It's a network. Okay, we proceed. Oh, please, can you hear me? Give some reactions so that I know. If not, I do not know if I should proceed or I should come in. All right. So I can't tell. Okay, yes, Mr. Emmanuel. Thank you. Okay, looks like. All right. So we continue. So then, as I was saying, in order to calculate the expectation of the events occurring, is just giving us this, what you're seeing on the screen. And that looks like a complex formula until you come to realize that it is literally each individual probability over the total probability. That's the expected value, over the total frequency. Yes. And that's what the expectation will be. So the expectation will come on the next page, but currently look at that for 5. It says that the probability of we taking an age and then that age being x1 is just the number of people who are x1 years old, which is 19 people, 5 people, that's people 19 years of age. So 5 out of the total, which is 24. And the probability of we taking a person who is 20 years old is 7 over 24. Like these are what we have learned in the previous chapters. The expectation, however, is going to be this. Oh, come on. Good. The expectation, however, for taking any particular value. So, for example, for taking any of the values, like the probability of taking an age of 19, will be given as the number of 19s present times the value itself, 19. I'm sorry. All right. Sorry for that. Right. Okay. Okay. So as I was saying, the probability or the expectation, as we were talking about at first, talks about the probability of each individual event occurring and how likely each one is to occur in the given outcome. Mostly, it is done for events that have somewhat of an equally possible outcome, or they may have varying outcomes. If they have equal outcomes, they have varying outcomes, it doesn't really matter. Expectation can be calculated like in the case of a Ludo die. The expectation of a value such as 1 occurring, or the probability of 1 occurring, will just be given as the probability of 1 occurring, which is 1 over 6, times the value 1 itself. So then the expectation of 1 in that case is just going to be 1 times 1 over 6. Then the probability expectation of a value 2 occurring is going to be 2 times 1 over 6. expectation of a value 3 occurring is going to be 3 times 1 over 6. Expectation of a value 4 occurring is going to be 4 times 1 over 6. So then the expectation of all the faces on the Ludo die occurring. So let's say all the faces on the Ludo die occurring are labeled as X. Anyone is labeled as an X. Then the expectation of X is going to be 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. In other words, it's the same as the sum of all the values divided by the total number of faces. So it's going to be 1 times 2 times 3, 1 times 1 plus 2 plus 3 plus all the way to the end divided by 6. Let me use a simple example to demonstrate. So we are going to look at the face of a Ludo die, the expectation of all the events on a Ludo die occurring. And then, okay, so we are close to stop time now. So Mr. Evans will take over any second from now, but I think we can still squeeze in this small example before we proceed. Okay, so I believe you can see my share screen now. So I'm sharing my board and then we can check from there. Okay. So then, here's an example. On the face of a Ludo die, we know that the possible outcomes are 1, 2, 3, 4, 5, 6. So now let's say the probability of any of these events occurring, let's denote that as the probability of L, which means the probability of the face of a Ludo die occurring. Okay. The expectation is going to be the probabilities here. For 1, we know it's 1 over 6. The expectation of that particular probability is going to be given as 1 over 6 times this value itself, which is 1. That's the expectation of 1. However, the expectation of L, which is the total set, is going to be the sum of all the expectations of the individual values. So if I was asking you the expectation of 1, then you are going to just give me so if I was asking for the expectation of 1 occurring, all you are going to give me is 1 over 6 times 1. However, the expectation of the total sets or the universal sets occurring will be given as 1 over 6 times 1. That's added to 1 over 6 times 2. Add that to 1 over 6 times 3. Add that to 1 over 6 times 4. And add that to 1 over 6 times 5. And finally, add that to 1 over 6 times 6. So then all these individual events summed up is going to be the total expectation of the set. So like this. So then you're going to have 1 over 6 times 1, which is still 1 over 6. 1 over 6 times 2, that's going to be 2 over 6. Times 3, that's 3 over 6. Times 4, that's 4 over 6. Times 5, that's 5 over 6. So then you're going to have something that looks like 1 over 6 plus 2 over 6 plus 3 over 6 plus 4 over 6 plus 5 over 6 and plus 6 out of 6. So then adding this together, what you're getting is 1 plus 2, that's 3. 3 plus 3, 6 plus 4, 10. 10 plus 5 is 15. 15 plus 6, and that gives you 21, all divided by 6. And you may rewrite this as a decimal value. So let's see, as a decimal value, what do we have here? So let's see how many times 6 goes into 21, shall we? 6 goes here 3 times, that's 18, and we are left with 1. So we bring a point here. Sorry, 8. Did I just subtract 18 from 21 and get 1? Okay, so we are left with 3. 6 is unable to divide 3, so you use a point to bring a 0. 6 goes here 5 times, so 6, 5, 30. So this means that our expectation will be 3.5 for this particular set of events. All right. So now let's use the example that was in the slides, and then let's work the expectation for that. Now, according to the examples, there is a class of people, and then their ages are given as 5 are 19, 7 are 20, 10 are 23, and then 2 are 17. So in the total number of people in the class, we have 5. And those 5 people, so let's use the table they used. So then we have people who are 19-year-olds. We have people who are, let me see, 7-year-olds, or no, 20-year-olds here. We have people who are 10. We have people who are 23, and we have people who are also 17. And it says the number of people who are 5 is 19 is 5. The number of people who are 20 is 7. Number of people who are 23 is 10. And the number of people who are 17 is 2. Now, if we are supposed to calculate the expectation or the total expectation of this set, remember that it's going to be the individual expectations combined. Just like the face of the little die, the expectation of any phase happening is just going to be the value times its probability. So then over here, we have to know the probabilities for these individual figures. Now, unlike the first one where each chance was equally likely, so we have 1/6 for all, over here, in order to know these guys, we have to find the probabilities for each individual event. So then the question mentioned that, let's say each event is labeled as X1, this is X2, this is X3, and this is X4. Then the probability of an event like X1 is going to be X1's number of ways of X1 can occur, which is 5, over the sum of the individual events, which is 5 plus 7, that's 12. 12 plus 10, that's 22. 22 plus 2, that's 24. So 5 over 24, that's the probability of X1 occurring. We do same for the probability of X2 occurring. That's going to be 7 over 24. We do same for the probability of X3 occurring. That's going to be 10 over 24. That may be simplified. And then we do that for the last one. That's going to be 2 over 24. So then this is not just the probability of X1. That was 5 over 2. So this is just going to be the expectation of X itself. So then putting these values together, we are going to have, let me clear space for this, 5 over 24 added to 7 over 24. So let's just do the addition straight ahead. 5 plus 7 gives 12. 12 plus 10 gives 22. And 22 plus 2 gives what? 24, right? So then that gives us a total of 24. I'm sorry, look at this. So then in order to calculate the expectation, all right, I almost messed this up right now. Good. So then we have these values. In order to calculate the expectation, we have to take each individual value times its probability and then sum them up to get the expected value, which is E. So remember, for that of each event is given right here. Okay, I want you to take note of that because I'm going to clean that so that I can use the space to work the rest of the question. So then, in order to find the expected value of X, the expected value of X is going to be given as the individual expectations all summed up. So remember, X talks about any of these events occurring, and then we have broken them into X1, X2, X3, X4. The probability of it happening in X1 is going to be 5 over 24. So then the expected value of that guy is also going to be 5 times the 5 over the given 24. That's the expected value for the first X1. And then we sum that up with the probability of the next one occurring, the expected probability of that occurring. That's going to be 7 times 7 over 24. You do all this all the way to the end, actually. So then the next one, probability of that occurring also is going to be, we are using the wrong values. Sorry. So then the probability of the age 19 occurring is going to be 19 times the 5 over 24. So remember, 19 corresponds to 5. Just like in the face of the Ludo die, each probability was 1 over 6, and then the individual values were given. The first one was a 1. So then its expectation was 1 times 1 over 6. The second was a 2. Its expectation was 2 times 1 over 6. So over here, the first value is a 19. Its expected value is going to be 19 times its probability, which is 5 over 6. I hope that is clear. All right. Then we add that to the second one happening. That is 20's expectation. So 20 times the probability of 20, which is 7 over 24. We do same all the way to the end. So then the probability of 23 occurring is also going to be, the expected probability of 23 occurring is going to be 23 times 10 over, over 24. All the way to the last one, 17 times 2 over 24. So calculating all these things and summing them up is what gives you the expected value. Okay. So then the expected value is always calculated by multiplying each value by its probability. So it doesn't matter what the values are. As far as they are given in the probability, you multiply them by their individual probabilities, sum them up to get the total expected value. And for each individual expectation, it's just going to be the value times its probability. And then you find its value. So this is the last part of the slide, okay? I don't like teaching mathematical subjects when I'm pressed for time, because whenever I do, I realize that I start to fumble, of course. But then I believe that the information has been put across quite well. If you have any questions concerning this, our time is up. You may go ahead and then ask before I end it. So ask any question concerning the expectation you didn't understand, and then I can take a portion of it quickly. Okay, so then since no hands are up, I'd like to believe that you either understand it too well or are too shy to talk. Either way, that is that. So I'll use one more example to explain expectation, assuming there are people amongst us who do not understand it. And this time I'm going to use a coin toss. That one has fewer values, and I believe in the case of a coin toss, since we have fewer values, there will be more space to move about on my board here. So then, when tossing a coin, the probabilities are ahead, the possible events are ahead and a tail when we toss it once. The probability of a head occurring is going to be, so then let's say the probability of any event occurring from this set here is giving us the probability of tossing a coin. So let's say the probability of C, okay? So now probability of the coin being tossed, being a head, is giving us 1 out of 2 chances. And then the probability of that coin being tossed, being a tail, will be also giving us 1 out of 2 chances. 1 over 2 like this. The expected probability for C, in other words, the expected probability or the likelihood of C itself occurring in total, that's the sum of the expectations of a head occurring plus that of a tail occurring, is going to be expectation of a head. And we know that the expectation of these events, that's expectation of a head occurring, is going to be number of heads present I'm sorry, a call came through. Okay, let's continue. And then the expected probability of a tail occurring is going to be the number of tails, which is 1 times 1 over 2 as well. And that also gives you a value of 1 out of 2. So then the sum of the expectations in this event is going to be 1 over 2 plus 1 over 2. And that gives you the wanted total answer. Okay, Mr. John.
Hello, sir. Hello. Please, I don't know if it is my end. I can't see your screen, man.
Oh,
I cannot see your screen. I don't know if it's my end.
Oh, okay. Let me check that and see. Oh, I think that is true. Oh, shit.
I don't know if my colleagues can see your screen.
Yeah, okay, sorry. I realized that yes, it is true. It is a fault from this end. All right. How about now? You can see it, right?
Yes, yes.
All right. Sorry. So let me redo what I did using another example, and then you see. So then I was saying that let's assume there is a set, okay? A set of ages of people. Let's use a set of ages of people in a class again. So then there is a set of ages of people in a class. And then in that class, we say the ages are 2. There is 4. And there is a 3. There is 2. There is 2. There is 3. And there is 4. So then from this set, you can obviously see that in the class, some people are 2-year-olds, then there is 1, 2, 3 of them. Some people are 3-year-olds, and there is 1, 2 of them. And then some people are 4-year-olds, there are 2 of them. In order to calculate the expectation of this, so let's represent their ages as an A. So let's say all of the sets of ages is an A. The probability, the expectation of A is going to be given as, so the expectation of A is going to be given as the number or the expectations of every individual element in A, all summed up together. So then let's check the expectation of a 2 occurring. The expectation of a 2 occurring is going to be the number of 2's present times the probability of 2. The 2 times the probability of 2 occurring. So then, what's the probability of 2 occurring? It is 1, 2, 3. In how many chances? 1, 2, 3, 4, 5, 6, 7. So then the probability of a 2 occurring amongst the ages is going to be 3 out of 7. Like this, 3/7. So the expectation is going to be 3/7 times the value 2 itself. That's the expectation of 2. Now we can check that for every single value here. Let's check the expectation of 3. The expectation of 3 is also going to be the probability of 3 times 3 itself. So that's going to be 3 times, what's the probability of 3? That's 2 3's out of the total number, which is 3/7. 2/7. And then finally, we check the expectation of a 4 occurring. The expectation of a 4 occurring will be the number of the probability of a 4 times a 4 itself. So that's going to be 4 times the probability of a 4. So how many 4's are here? There are 2 4's out of the value 7, like this. So then we multiply the first set. 3 times 2 gives us 6, and that's out of 7. Add that to the next set. 3 times 2 gives you 6 out of 7. And the final set, 4 times 2 gives you 8 out of 7. Sum these up and then you are getting the numbers. So 6 plus 6 is 12 and 12 plus 8 is 20. So 20/7. The expectation is what we have calculated for with this. So then simply put, the expectation is basically each probability times the value. So each respective probability times its value gives you the expectation that you are looking for. So then 20/7, or you may convert that into a decimal form. So I hope this makes the concept of expectation clearer. Now, expectation is actually stepped up. The higher up we go in the slide, you realize that, okay, expectation of a random variable, if it is discrete and if it is continuous, it follows a different approach. So what we are looking at right now is mostly for discrete values. But then for continuous values, it also takes a different turn. But then the basics of it is the discrete, and then it's quite simple. All right. So then, are there any questions pertaining to this now? Our time is up, and then we are definitely stopping right here. I have not seen the tutor for it joined. I believe he's giving me time, so I am going to end it right here. So are there any questions concerning expectations? Okay, so looks like there are none. So I'd like to believe that the lesson has been understood. I will share some questions on the platform. Last time I did say that I will, but I didn't. But I am going to share the questions on the platform today. And then when they come, you may attempt them and then drop your answers right there. And then we will address any mistakes that there will be. And then you will see if there are some concerns that will be raised alongside, and then we also address them. So then give the next tutor about 5 minutes. He will join shortly, and then he will take over from where I left off. Thank you for being a good listener or a good learner tonight. Goodbye.